Okay, let's get started. So today we're going to start with our core material review, modeling and solution methods. Normally I'd ask if there's any questions at the beginning of the class, but there's been one class, so very unlikely. There's a lot of, I think, chapter 2, but it really kind of varies. So for the next few weeks, what we're going to be focusing on is first, today, Laplace transforms, and if it spills into our first class next week, that's okay. Then we're going to go over transfer functions, block diagrams, and then we're going to go through, so that's really the solution method part of it, I would say, and the modeling. We'll have mechanical systems, electrical systems, and then electromechanical. Systems. I'm probably not going to teach too much in terms of thermal or fluid systems, but we could also do those if we wanted to, but that's more 33 material. So these are topics that hopefully everyone is familiar with here. Laplace transforms, I expect everyone has seen those, at least 2 or 3 classes at this point. Transfer functions, block diagrams, those would have been in 3333. And mechanical systems, electrical systems, you guys have seen that probably since like freshman or sophomore year, I would say. So let's start by just spending a day to review Laplace transforms. So let's say we have a system that is modeled, by the following equation. A2, y double dot, where the dot is for a derivative with respect to time, A1 y dot plus A0 y is equal to B0 times U. So in here, U is a input, probably a control input. It's a function of time. Y is also going to be a function of time, but that's going to be our output. Y dot is dy over dt. It's a derivative with respect to time. Right. A0, B0, A1, and A2 are our parameters, which we're saying are constant. And then we also have initial conditions. I guess I'll write it out. Initial conditions, y0 and y dot 0 are known, let's say. All right, initial conditions, I'll typically just write ICs in the future. All right, so let's go through and just review some basic concepts here. Can we have any descriptors? Like if we were to categorize this type of equation, how would you guys categorize it? Any ideas for that?
Second order.
Second order, okay. Why is it second order? Right, so because of the differential, right? The derivative. Second order. What else? Linear, good. Anything else? Ordinary, good. Would be homogeneous. And then in the chat here, so the way that I would define this is it's not time variant. This is time invariant. Right? Time variant is if our parameters were to vary with time. The things that are multiplied by either u or y, right? If those vary with respect to time, I will categorize that as time varying or time variant. If the parameters are constant, essentially the things that are in front of our u's and our y's in this case are constant, then it is time invariant. So we're going to be working a lot with equations that are going to fit into this category here, except for the second order thing. We'll have different orders that we go through in this class. All right, so good. So you guys are pretty, you guys remember a lot of that stuff. So can we predict our output if we know our input? And if so, if yes, well, how? And if not, why can't we?
Yes.
Okay, yes, why? Or how, rather?
We have the model equation, so let's take the transfer.
So will we get the transfer function? We could, but transfer function is more of a model. We'll get into that next class, but I would categorize the transfer function as an alternative model to this representation. Laplace transform, right? And an inverse Laplace transform. That's one way to solve this. Is that the only way? What are other ways that you guys have learned?
Differential equations.
Yeah, so I'm hearing something about like x is equal to e times something, right? You gotta be careful because that is for a very specific condition. for that solution, right? Those E's may not show up in the same way depending on what type of input term we have, right? You're probably thinking of the homogeneous case first or second order solution. I think I heard somewhere over here, you guys are gonna have to forgive me. This is a much bigger class that I'm used to, so it's gonna be hard for me to identify for the first few weeks who's answering what. I heard over here something about like the differential solution method or something like that, right? Trial solution method could work. That's probably what somebody was thinking of there. Is that the only way? Laplace transforms and inverse Laplace, then trial solution method. Any other ideas? That's it. There's no way that you guys could figure out how to solve this otherwise. Nothing? MATLAB? Okay, I'm waiting. I was waiting for that answer. You're getting closer, right? I'm not looking for MATLAB specifically. MATLAB can do what the answer is I'm looking for here. Numerical methods, that's the answer I was looking for, right? MATLAB has one way to do that, right? The numerical methods not be an exact solution, right? But they may be able to reformulate this into some sort of matrix inversion problem or something like that and approximate our solution, right? But we can in this case, because it is linear second order, well, the second order doesn't matter too much, because it's linear time invariant, we can solve this analytically. All right, so definition of our Laplace transform. All right, Laplace transform, I'm a variable little x here, which is a function of time, is equal to the limit of big T approaching infinity of the integral from 0 minus, usually we just say 0, but just right before 0 to big T of x, which is again a function of time, times e to the negative st dt. All right, and this is skipping over a handful of things for the actual definition of our Laplace transform, but it's close enough for our purposes here, right? So this is our definition for a Laplace transform, where S is a complex variable that relates to frequency. All right, so let's assume we have no initial conditions for the time being, right? If we have that case, then we can cancel out this 0 minus term here. So honestly, we're going to do that for the most part for our purposes. We're just going to say we're going to make it easier on ourselves. Laplace transform of x, or x of t, if we want to write that out, is the integral from 0 to infinity of x of t e to the negative st dt, or we could also write that as capital X of s, right? And then the inverse Laplace transform, little x of t, is the inverse Laplace transform of big X of s, right? Laplace transforms are invertible, right? What type of systems can we use Laplace transforms for? What are they limited to? Or what are some systems or sets of equations that you definitely can't use a Laplace transform for? Nope. Well, time varying, those ones get very complicated, but they may be able to be done. But nonlinear systems, we cannot use Laplace transforms with nonlinear systems. So if we have like a y squared or a y times u or anything like that, Laplace transforms are not appropriate, right? So these are for linear systems only. All right. And we'll focus in this class on linear time invariant, or LTI, systems. If we had a nonlinear system, what we would have to do if we want to use Laplace transforms desperately for it, we'd have to linearize it, probably about some sort of equilibrium, and then do a Laplace transform for the linearized system. But that would, of course, be approximate. Okay, so a basic example for a Laplace transform, x of t is e to the negative at. T is going to be greater than or equal to 0, right? And we're going to just say x of t is equal to 0 or t is less than 0. These are just a handful of different things that you're supposed to go through. We're not usually going to focus on these types of details here. We just want to kind of review it. So we want to solve for the Laplace transform of x of t or big X of s. All right. So we would plug that x of t into the equation that we had for above and get x of s, right? So x of s, which is the Laplace transform of little x, Laplace transform of e to the negative at, we could also write it as our Laplace transform definition is 0 to infinity of that x of t, e to the negative at here, times e to the negative st dt. And all we need to do is evaluate this integral and figure out what big X of s is. So what is big X of s? I'll take it just a minute, work through it quickly, see if you remember how to deal with exponentials with infinity in them. And I guess I should say here, as a caveat, a is going to be a positive number, which means the exponential on the top there is negative. Seeing about 50% people that aren't even moving. So is it because you guys know what you're doing or you really don't know what you're doing? Which one? Fair enough. Okay. Well, for the one honest person, let's help them out. What do we start with for this? Group the exponentials together. Good. All right. That's probably an easy first step here. So we should end up with e to the what it ends up being up there. You guys are whispering. I can't hear you. Negative a minus s. Negative a minus s all times t, or let's just group them together maybe here, right? Negative s plus a times t, right? Okay. All right. Now what do we do? What is the integral? And I forgot the dt here. What's the integral of this with respect to dt?
The whole expression over
All right, at least you're trying. What is it? 1 over s plus a? Question mark? Closer. Gotta bring the negative with it, right? So 1 over, I guess we could put it down there, but 1 over s plus a, right? Is that it? Okay, and then we need to evaluate it at 0 and infinity, right? For t is equal to 0 infinity. right? Okay. So what do we end up with? Let's go through it step by step, but yes, that's where we're going to end up with here. So we're going to have e to the negative s plus a times t, where t is infinity, minus e to the negative s plus a times 0, right? Okay. If a is positive, which I mentioned earlier, let's go with the easier one at first, e to the 0. It's going to be 1, so we have a negative 1 here. What's going to be e to the negative s plus a times infinity? 0. Okay, and we end up with 1 over s plus a, right? So Laplace transform of e to the negative at is 1 over s plus a. Yeah.
Let me see the question. Why does that end up as zero?
So it's e to the negative infinity, right? If e has a positive infinity of the exponential, obviously shoot off to wherever, right? But e with a negative infinity in its exponential will decay down to 0, right? Exponential decay is what it is. All right. So this is how we do Laplace transforms, right? But thankfully, we don't need to go through this procedure every single time, right? Because as long as we know what functions we're dealing with, if somebody in the world did a Laplace transform for a certain function once, it works all the time, right? So others have already done Laplace transforms for some important functions. Right? Our Laplace transform tables, which I'm sure you guys have all seen a lot, right? So let's just go through a few important ones. I'll go through the name of the function, what x is equal to, and then what x of s is going to be, our Laplace transform for it. So we'll start off with our impulse, or I'll say specifically our unit impulse. Unit impulse is represented by the fancy d as a function of time, the Dirac delta function, right? And Laplace transform of that is literally just the number 1, right? An impulse looks like as a function of time, if this is t is equal to 0 right here, right? The magnitude of its output will be infinite for a very brief period of time, an infinitesimally small amount of time, right? It's an impulse, it's an impact event, right? The next one be our unit step, one that we're going to use quite a bit, actually both unit step and unit impulse, right? Unit step is just a constant of 1, right? It's usually represented though, sometimes by u subscript s times t, sometimes also like a theta as well in some cases here. But we could also just say it's just 1 in this case. Laplace transform for a unit step is 1 over s. All right. What a unit step looks like is that before time is 0, it's nothing. And then we step up 1 unit to a value of 1. All right. That's where it gets its name from. All right. Another one that we just did, our exponential. That's e to negative at, which we already just proved 1 over s plus a, right? We also have our sine waves and our cosine waves. Where if we have sine to the bt, where b is our frequency, or cosine bt, they look very similar. Sine has a b over s squared plus b squared. Cosine has an s on top instead, s squared plus b squared. All right, and there's many, many other Laplace transform tables out there available, right? some programs even can do it moderately successfully. Depends on how complex of a system you're looking at though, right? So people have done this before, which means we're not really going to need to go through this procedure here in most cases, right? People have already done our common Laplace transform, so we don't need to, unless we're doing a very special type of an input. All right, so Laplace transforms have certain properties. Let's say we have functions f and g, which are both functions of time here, right? A and b are constants. The Laplace transform of f is going to be big F of s. The Laplace transform of little g as a function of time is big G of s. All right. You guys should be familiar with some of these properties here. All right. We have a Laplace transform of a times a function f. Right. We can take that little a out. We can take a constant out if it's multiplied by another function of time, which means that this is going to be a times F of s. Right. So you can take constants out of a Laplace transform. If you have two functions, you're adding together. Right? You can separate your Laplace transform for different additions and subtractions. So in this case, it's addition. Laplace transform of f of t plus the Laplace transform of g of t, or f of s plus g of s. Right? And then if we want to combine these two cases, just as another example, we have a f of t plus b g of t. We can go through and separate these. First, let's separate it into, take out that constant times, well, let's actually separate it out to Laplace transform of a f of t plus Laplace transform of b g of t. We know we can take out a and b here, and we can end up with a f of s plus b g of s here, right? These are all properties, and they also work for our inverse Laplace transforms. They have the same exact properties as this. These are all due to the fact that we are dealing with linear systems here. Doesn't work for nonlinear systems. All right, so another example here. Let's say x of t is 16 times the sine of 12t plus 22e to the negative 4t. All right. Find x of s. All right, so let's try this again. I'm going to try and leave this table up here for you guys here. But just take a minute. Shouldn't take too long with the table already up there. But tell me what the Laplace transform of this function should be. So what are we getting? 192 over what was it?
Plus 144
Mm-hmm.
plus.
16 times 12, that's 192, right? I think that's what it should be. Does anybody have questions on this part? All right, this should be pretty straightforward at this point. All right, just reviewing Laplace transforms. That looks good to me, right? What about Laplace transform for something that we're going to probably use a little bit more commonly? -2 over s plus 5 plus 3 over x minus 7. Let's actually do inverse Laplace transform is what I meant to say. We want to find x of t. So what is x of t going to be in this case? Let's walk this one through together, I guess. Let's do that. Just don't want to sit here in silence the entire time. Just decent part of it. All right, so x of t should be an inverse Laplace transform of x of s, right? So we have an inverse Laplace transform of this thing that we just wrote out. Right? What do we do from here? What is our next step? I can't hear you at all. You're in the back of the class. Please try again. Okay. So we're going to use those same properties we had before. -2 over s plus 5 plus inverse Laplace transform over 3 over s minus 7, right? Good. What will we do next? I heard someone else over here. Move things outside, right? So that -2 can come out. What we're trying to do is get things that to be in the form of the table that we had earlier, right? Now we have things that are in the form of that table from earlier, right? If we have 1 divided by s plus a, we know what the inverse Laplace transform of it, just going to be that, right? So we're going to have -2, and then it's going to be e to the what? -5 times t, right? Plus 3 e to the what here? Positive 7t, right? We have a -7 on the bottom there. Good. All right. Another example. X of s is equal to 11 over s plus 2 times s plus 3. Find x of t. Okay. So ideas for this one. Partial fraction expansion isn't the name of it normally, or decomposition, I guess. Oh, I'm going to call it expansion. So partial fraction expansion, right? But let's go through this step by step to get there, right? Partial fraction expansion says that, well, first of all, even before we get to that, x of t is equal to the inverse Laplace transform of x of s. 11 over s plus 2 times s plus 3, right? What's the problem with this? At least for the context of this class, this isn't in the chart, right? We can't just separate the two parts on the bottom to be two separate exponentials, at least not yet, right? We need to use partial fraction expansion. Seems like you guys remember what that is. So just take a crack at it, apply it. Use partial fraction expansion. And tell me what we get inside of the inverse Laplace transform. I don't want the final solution. I just want what's in there. A over s plus 2, b over s plus 3, good, right? And we need to solve for those a's and b's. right? That's the key with partial fraction expansion. So I usually use instead of A and B because those mean something different in state space modeling. We're looking for C1 and C2 is usually what I call them. And we need to solve for those. So what we get? Anyone get C1 or A, whatever you want to call it? 11? 11 and negative 11. I agree with those numbers, right? If you guys don't remember partial fraction expansion, if you like look me up on the Texas Tech website, you'll see that I have like my own lab website under my tab, right? And then go to like the teaching section. I have like 2 videos I want to say on partial fraction expansion. You want to use that to review it if you don't remember the exact steps for it, right? But we end up with something like this, which means we can do an inverse Laplace transform of 1 over s plus 2. And we'll take out the negative 11 here. And 1 over s plus 3. And it's pretty straightforward. We're going to end up with 11 times e to the negative 2t minus 11 e to the negative 3t, or 11 times e to the negative 2t minus e to the negative 3t. Yeah, if you need review videos for that, I mean, there's hundreds of resources, if not thousands of it online. But I can point you in the direction of my videos if you want to use those instead. They're just, at least for one of them, because it's built in 2020 in the middle of the pandemic. It's a boring video, very boring, but it goes over what we need to. All right, so partial fraction expansion, right? Let's now switch gears just for a second and talk about one more type of Laplace transform that's valuable. Well, we'll go through really 2. And I'm not, I guess categorizing this as a Laplace transform isn't the right way to say it. It's more of using a Laplace transform. And it's called the final value theorem. Anybody remember what the final value theorem states? Let's say for a variable x that's a function of time. Nobody? All right, that's okay. This one's going to be important. So I recommend memorizing it at some point. The final value theorem says that x, as t approaches infinity, right? Or sometimes I'll just write as x of infinity here, or maybe x of steady state, xxs, right, is equal to the limit of s approaching 0 of s times x of s for certain conditions, which we're not covering just yet, but it has to do with stability. The opposite way? What do you mean? So that is the initial value theorem is what you're describing. I don't use that one very often. So you're probably not going to need the initial value theorem in this class, but yes, there is a sibling function to this as well. But final value theorem, we're going to use a lot because that's going to be our criteria for our controllers a lot of time. All right. So that's one to memorize because we are going to use that a decent amount, including in the first homework, just as a review. And I don't know, I guess the final group of Laplace transforms that are very useful for dynamic equations, if we have Laplace transform of x of t is big X of s, the Laplace transform of x dot, which is the same thing as dx over dt, is equal to s times x of s minus little x at 0, right? This is our initial condition for x. This is capital X of s, that's our Laplace transform. And then this is s, that variable there, right? Derivatives are associated with an s multiplied by the function, right? But don't forget this initial condition. We won't probably use it too much in this class. We'll probably assume that's 0 in a lot of cases here, but you should always keep that in mind. That initial condition is there in a lot of actual real world cases, right? Not everything starts at 0. Laplace transform for x double dot would just be applying the same logic to this guy right here. And what we'd end up with is s squared x of s minus s x0, and that's a little lowercase, and then little x dot 0, right? For our other initial condition, because we have 2 derivatives, we probably need 2 initial conditions. All right. And then we won't use this one as much, but it will come up from time to time. For an integral from 0 to t of x of tau, so x as a function of tau here, we're replacing the t with tau, integrating over that, it's going to be x of s over s, right? Derivatives and integration, they look like the opposite, right? Derivatives, we're multiplying x of s times s. Integration, we're dividing by s, right? In terms of important functions to memorize, right? Like, obviously, you can look all this stuff online. You can put it on a study sheet and stuff like that. But I would definitely know this one because you don't want to waste time looking this up. I would definitely know the final value theorem as well. And then for sure, these guys right here. They will be very common, so you might as well just learn to use them now, right? All right, this second one here, this one isn't a bad idea either. And this one will come up in the last half of this class or so. All right, so remember where we started. We had a second order differential equation, right? Where I asked, if we knew what u is, can we solve for y and predict what's going to happen to it, right? We said, yes, we could use Laplace transforms and inverse Laplace transforms. So let's use what we just covered here to do that, right? So our earlier dynamic equation a2 y double dot plus a1 y dot plus a0 y is equal to b0 times u, right? We're going to take a Laplace transform of this entire thing, right? We're trying to solve for y as a function of time here. The first step, take a Laplace transform of everything because it's going to be easier to work in that world than in the time domain world. All right, we can break up this Laplace transform into separate pieces. Right? We're trying again to solve for y as a function of time. Right? Let's start with this guy right here, and then we'll go to this side, and then we'll worry about the right side after. Laplace transform of a0 times y. How do we want to represent that? A0 times big Y of S, right? Because that's what we're going to be solving for, is that big Y of S. What about the term over here?
A1 as capital Y. B initial. Minus.
Okay, is that right? Did I write it the way you wanted me to? That's correct. Need parentheses, right? The A1 is in here. We would pull it out, right? So the A1's got to be multiplied by our initial condition as well here. Right? So it's got to look like that. And for this one, we apply that same logic. So it's going to be A2 times S squared Y of S minus S Y0 minus Y dot 0. Right? What about the other side? Say again? All right. Did I give what U of S is at this point? No, I haven't. Right. So it's just a generic U of S for the time being. Good. All right. Okay. We're trying to solve for Y as a function of time. What's our next step here? Initial conditions are already in there.
What is it? Y dot and Y0.
That's this is little y and little y dot, right? I heard somebody else say the right thing. It's over here. And that's on over there, but sure, yes, right? We're going to combine all the terms that are multiplied by Y of S, right? So what is multiplied by big Y of S here? A2 S squared, A1S, and then A0, right? That's all Y of S. Really what we would do is we'd break it up step by step. I kind of want to skip over that, right? Is that it? Is that all we're going to have on this side over here? We still have all those initial conditions, so they still got to exist. So we'll just have negative A2 S Y0 minus A2 Y dot 0 minus A1 Y0 is equal to B0 U of S, right? All I did was I skipped over expanding out all these terms, right? I combined all the Y of S's terms together, and I left the rest of these over here. And actually, we could group those two Y initials together as well. So I'll write it out one more time here. And then we're going to have A2 Y dot. And then let's group in those last terms, A2S plus A1 times Y0. Okay. Now that we've done this, what do we need to do next? Right? So we got to take all these things, bring them over to the other side, and then solve for Y of S, right? So Y of S times all that junk that's in front of it, right? It's going to be equal to A2 Y dot of 0 plus A2S plus A1 Y0 plus B0 U of S. We're going to divide by the junk that's over here. And so we're going to end up with Y of S is equal to all that stuff divided by A2S squared plus A1S plus A0. Right? And typically, the way that you'd represent these things here is you wouldn't group all these together. I'd do A2 Y dot of 0 over A2 S squared plus A1S plus A0. And then I'd have this numerator term here divided by that same denominator. And then B0 divided by that denominator times U of S. Right? Okay. Are we done? Did we accomplish what we needed to? What we do need to do for our last step. Inverse Laplace transform, right? Oops. Okay. Inverse Laplace transform of all these things here, which we can separate out into 3 separate pieces, right? I don't want to write it out all again, but actually we could just do it like this. Laplace transform, inverse Laplace transform, and then inverse Laplace transform of this piece. That goes there. This piece goes here. This piece goes here. Okay. Could you completely solve for YT based off of the information I've given you? What do you think? For the context of this problem, we're done. But could you actually get YT as a function of time? What are we missing? No, not numbers. Close, but not quite. Initial value, those are just numbers again, that same category. Still numbers. Input, right? I haven't defined what the input is, right? So how can you take an inverse Laplace transform of something that you don't know what it was in the first place, right? So that's what we're going to do next time. We need to know U of S before applying the inverse Laplace transform. For the last term. The first 2 terms, you can do inverse Laplace transforms of these right now, right? You guys know how to do partial fraction expansion? You do it for those 2, and you take the inverse Laplace transform after that, right? First 2 you can do, but the last one, we're going to have a challenge of doing the inverse Laplace transform without defining what that U of S is. So that's what we'll continue off with next time. All right. That is it for today. Enjoy your weekend. No class on Monday.
I remember both. Oh, yeah.